Buenas tardes a todos y bienvenidos a esta conferencia del tercer ciclo sobre astrofísica y cosmología, titulada La estabilidad a largo plazo de los sistemas planetarios. Voy a hacer una breve presentación de la conferencia y del conferenciante. Hasta hace poco menos de 20 años, el único sistema planetario que conocíamos en nuestro universo observable era nuestro sistema solar, que es una compleja familia, como todos saben, con una estrella central, 8 planetas, centenares de miles de asteroides, millares de cuerpos menores, toneladas de polvo interplanetario y millones de cometas. Pero en 1995 se descubrió el primer planeta en órbita en torno a una estrella diferente de nuestro Sol. Hoy sabemos que existen más de 1000 planetas extrasolares y más de 800 sistemas planetarios, muchos de ellos con 3 o más planetas. Y la lista de candidatos podemos decir que crece cada día. Un problema clásico de mecánica, como es el estudio de la estabilidad de la órbita de varios cuerpos en torno a un objeto central, ha cobrado en este contexto un auge que es lógico de entender. Este problema no se limita a entender la evolución pasada y futura de nuestro sistema solar, sino también la estabilidad a largo plazo de sistemas planetarios extrasolares. De esa estabilidad, entre otros factores, es muy posible que dependa el desarrollo de actividad biológica en alguno de los planetas que los formen. Hoy tenemos el honor y la suerte de que nos acompañe el profesor Scott Tremaine, que actualmente ocupa la cátedra Richard Black de Astrofísica del Instituto de Estudios Avanzados de Princeton. El profesor Tremaine se graduó en la Universidad de McMaster en Canadá y se doctoró en la Universidad de Princeton. Ha realizado tareas docentes en el Instituto Tecnológico de Massachusetts y las universidades de Toronto y Princeton y fue el primer director del Instituto Canadiense de Astrofísica Teórica, cargo que ocupó entre 1985 y 1996. En el periodo desde 1998 a 2005 fue director del Departamento de Ciencias Astrofísicas de la Universidad de Princeton. Y su labor de investigación abarca estudios de la dinámica de objetos astrofísicos en contextos muy diversos, como la formación y evolución de planetas, cometas, agujeros negros, galaxias, y actualmente pues, está trabajando en el mundo de los exoplanetas, que es un tema candente en la astrofísica actual. Recibamos con un aplauso al profesor Tremaine, que nos va a explicar aspectos fascinantes de la evolución de los sistemas planetarios.
Thank you all for coming, and I would like to thank the Foundation for hosting this event. Before I start to talk about the stability of planetary systems, I would like to remind you about the solar system, since it's the planetary system that we know the best. This shows all the planets of the solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. It's a very good picture, but it's misleading in some ways. The planets are actually much more widely spaced than this. So on the scale where the planets are the right size, the distance from the Earth to the Sun should really be about 1 kilometer. The distance from the Sun out to Neptune should be about 30 kilometers. And the distance to the nearest star would be about 200,000 kilometers. So the solar system is very isolated, and the planets are very far apart. They're also much smaller, much less massive than the Sun. Jupiter is only about 1/1000th of the mass of the Sun, and Earth is only 1/300th of the mass of Jupiter. And finally, the solar system is very, very old. It's 4,500 million years old, and it will last for another 7,000 million years before the Sun dies. If we count that in orbits, since the Earth goes around once per year, it's about 5,000 million orbits of the Earth. Our understanding of the dynamics and the structure of the solar system dates back to Copernicus, who famously showed that the Sun, not the Earth, was the center of the solar system. So here's one of his diagrams with the sun working out Mercury, Venus, Earth, and the moon, and so forth. After this discovery by Copernicus, the next major advance was the German astronomer Kepler, who showed that the motions of the planets followed three empirical laws, that the orbit was always an ellipse, with the sun at one focus of the ellipse, that a line joining the planet and the sun sweeps out equal areas in equal times, and a relation called Kepler's law, which relates the orbital period of the planet to its distance from the sun. Planets at larger distances have larger orbital periods. His discovery about the shape can be made quantitative using a definition I'll use later in the talk of the eccentricity, which measures the deviation of the orbit from a circle. For a circle has an eccentricity of 0, and as it becomes more and more elongated, the eccentricity goes up towards 1. The Earth is very nearly a circle with an eccentricity of 0.0167. The third major player was Isaac Newton. He discovered the laws of motion for the planets. He discovered the universal law of gravity. He solved the equations of motion for the sun and one planet and was able to show that the solution to those equations gave a motion that obeyed all of Kepler's laws. Newton is such a famous scientist that for many years he was on the British £1 banknote, which showed Newton and some orbits of planets, but I want to stress that this is not correct because it shows that the orbits are ellipses with the sun at the center instead of at the focus. So it's a great honor to Newton, but I'm not sure he would have been happy. The problem that I'm going to talk about is the problem of the long-term stability of planetary systems, and it's very simple to state. You have a large mass like the sun, which is surrounded by some number of planets. They're on nearly circular orbits in almost the same orbital plane. Newton was able to solve the case where n is equal to 1, where there is one planet. But if there are multiple planets, each planet tugs slightly on the others because of their mutual gravity. And the question is, if you let this configuration orbit for thousands of millions of orbits, does it remain stable, or do the orbits gradually become more and more eccentric until something catastrophic happens? This is interesting. First, of course, it's one of the oldest problems in theoretical physics. Newton thought about it, so the problem has been around for 300 years. It's interesting because we'd like to know what the fate of the Earth is. There are really only 4 possibilities. If the orbit of the Earth is unstable over very long times, it may fall into the sun. It might be ejected into interstellar space. It might collide with another planet. Or if it's stable, we can be much more optimistic. We'll stay around until the sun dies, and then we'll be burned up as the sun expands at the end of its lifetime. All of these possibilities have been thought about in other disciplines. So, for example, Hollywood has thought about the possibility that we'll collide with another planet. And there's a famous poem by the American poet Frost, who says, "Some say the world will end in fire, some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction ice is also great and would suffice." So these are the only possibilities, and we would like to know what will eventually happen to our planet. We'd like to know why there are so few planets in the solar system. There are 8, but there could be 20 or 30. Why is it perhaps that other planets couldn't survive in the solar system, that the system is full and there's no room for any extra planets? On a practical view, we could use our understanding of the orbits to calibrate the geological time scale. Geologists can measure geological time from the fossils that they find at different depths, and by measuring the ratio of elements in the sediment in the seabed, they can measure the temperature of the oceans at different depths. And the changes in temperature of the ocean are largely driven by long-term changes in the orbit of the Earth. And if we can measure those long-term changes, if we can calculate those changes, we can calibrate the geological timescale so that we know, for example, that a particular dinosaur lived a particular number of millions of years ago. And we can also perhaps use the response of the Earth to changes in the amount of sunshine it gets due to changes in the Earth's orbit to understand better how the climate of the Earth works. And finally, physicists would like to understand how dynamical systems behave over very long times. This problem of the stability of the solar system was first thought about by Newton. His writing on it said that blind fate could never make all the planets move the same way in orbs concentric. That is, you have to explain why the planetary orbits are so nearly circular. But he says there are small irregularities, small eccentricities in the orbits which could have arisen from the mutual gravity of the planets upon one another, and which will be apt to increase until the system wants a reformation. And historians say that what this means is that he believed that the solar system was unstable, and that this belief was connected to his complicated beliefs about God. He believed that in a God that continued to intervene in the workings of the universe, and that, in a sense, that because of his laws of motion, God didn't need to make the planets go around, that they could go around fine on their own, but that that you had a service contract with God, and every now and then he would go in and tune up the solar system. This was not agreed to by all of his contemporaries, in particular Leibniz, who already had controversies with Newton because they both claimed to invent the calculus, said Newton and his followers have a very odd opinion concerning the work of God. According to their doctrine, God wants to wind up his watch from time to time, otherwise it would cease to move. He had not, it seems, sufficient foresight to make it perpetual motion. Another mathematician who thought about the problem was the French mathematician Laplace. Laplace made this famous statement that a sufficiently great intelligence that knew all of the forces acting in nature and the positions of all things of which the universe consists would be able to predict the motions of all of the bodies in the universe in one single formula, and to it nothing would be uncertain, both future and past would be present. This is the point of view that has come to be called Laplacian determinism, the idea that the laws of physics are so well defined that we have no free will, and that everything in the future, in principle, can be predicted from the present. And this point of view, of course, was inspired by the extreme success in understanding the motion of the planets. So how can we solve the problem that we've posed? Many famous mathematicians and physicists have tried to work on this. They've proved many very interesting and important results, but always in limiting cases that don't apply to the real solar system. To understand the real solar system stability, the only possible approach is to use a computer to numerically calculate the planetary orbits far into the future and far into the past. Why is this difficult? Well, first, you are trying to follow these for 10,000 million orbits. So even with the fastest modern computers and the best calculations, the calculation takes several weeks at least. Second, most of the improvements we hear about in computers in the last 10 years have come from parallelization, from splitting up the problem into many smaller problems that can be done at the same time on different computers. With the solar system, this doesn't work. You can't calculate its motion from 1 million to 2 million years until you've first calculated it from 0 to 1 million years. So you can't use modern supercomputers to do this. You may just as well use your laptop. You need very sophisticated algorithms to avoid the buildup of numerical errors. And the standard arithmetic that's used in most computers is simply not accurate enough. It doesn't carry enough bits, enough digits in the calculation to avoid the buildup of round-off error over these very long times. Nevertheless, you can try to do the calculation. All you need is Newton's law of gravity and Newton's laws of motion for the 8 planets in the sun. The equation is extremely simple to write down. There are some small corrections. These include corrections for the effects of the masses of the satellites of the planets, like the moon, for the effects of Einstein's theory of relativity, for some of the largest asteroids, but all of these are at a level of less than 1 part per million. There are also corrections that we don't understand. There are thousands of asteroids, and we don't know the masses of all of them. There are also bodies in the Kuiper belt beyond Neptune. The sun slowly loses mass, and we don't know the rate at which it loses mass. The solar wind, the mass flowing out from the sun, exerts some drag on the planetary orbits. We're embedded in the Milky Way galaxy, and it exerts some tidal forces. There might be passing stars that affect the system, although that's extremely unlikely. And we don't know all the masses of the planets, the initial positions and velocities. We don't know the effect of comets and so forth. But all of these effects are extremely small. They're all at a level of less than 1 part per 100 million. And what that means is that to a very high accuracy, we understand the solar system. It's an isolated system with a known set of equations. The starting conditions are known. All we have to do is put it into the computer and do the calculation. So in the last few years, people have managed to do this. This is an example of a calculation of the 8 planets. These pictures show only the innermost 4 planets, the Sun, Mercury, Venus, Earth, and Mars. Each of the lines represents its current orbit, and the dots are a set of images of the actual positions from a particular time interval. This is 50 million years into the future, 50 million into the past. This is just before the sun dies, 7,000 million years in the future, and just after the solar system was formed. And you can see that this is pretty boring. All the orbits look pretty much the same. There are no significant changes. All the planets are still there. It looks like nothing has happened, and the system is completely stable. This is not completely correct. The actual answer is much more interesting. But before describing this, I have to say a little bit about dynamics. One of the things we have realized is that dynamical systems can be divided into 2 kinds. There are regular systems. These are the systems that Laplace was talking about. They're very well behaved. You can predict them very well. Mathematically, that means that if you change the conditions of the system by a small amount, those changes will grow linearly with time. After time 1, the change might be 1 millimeter. After time 2, it's 2 millimeters. And after 3, it's 3 millimeters, and so forth. This predictability is the basis of many games, tennis, golf, pelota. It's what you see in the simple pendulum. If you took a physics course, every problem you did in a mechanics textbook is an example of a regular system. Planetary orbits in the solar system on short time scales are also regular. The other kind of system is chaotic systems. They're unpredictable. What that means mathematically is that small differences grow exponentially. So if the difference after 1 time unit is 1 millimeter, after 2, it's 2 millimeters, then 4 millimeters, 8, 16, doubling every time step. Examples of this, again, there are games like roulette, dice, pinball. The weather is a chaotic system. That's why it's hard to predict the weather beyond a week. Billiards, if you're trying to do a shot that involves bouncing off several balls, is also chaotic and hard to predict. But the simplest example is a system called the double pendulum. This is a video of the double pendulum. Basically, it's a single pendulum with an axle in the middle of it. When the person initially starts it, the axle is fixed, so it acts like a single pendulum and goes back and forth, very predictable, very regular. What he will next do is unscrew the axle, so you have two independent joints, one here and one here, and he will release it again. You can see that in this case, the motion is much more complicated and hard to predict. If you think you can predict it, try to predict the last time that the bottom pendulum will rotate through the top pendulum. And again, mathematically, what this means is that if he started it from a slightly different position, the difference would grow exponentially with the time. Okay, I think now it has pretty much come to rest. Okay, so there are these two kinds of system, regular and chaotic. We know that on short time scales, the solar system is very regular. We can predict the positions of the planets. We can predict eclipses. We can predict the orbits of the moon. We can send spacecraft to other planets. Everything is very regular. However, once physicists began to calculate the orbits of the planets over very long times, they found that they were weakly chaotic. That is, that small differences began to double every few million years. This is an example of the sort of effect that they found. In this case, they've done a calculation of the orbits of all the planets for 200 million years. That's only about 5% of the total age of the solar system. Then they did the calculation over again, and the only change they made was that they shifted the initial position of Jupiter by 1 millimeter. And then they plotted the difference in the position of Jupiter between the two calculations. And here they did it with 3 different numerical methods, and you can see that the difference is starting to grow, and every few million years, every 10 or 20 million years, the difference goes up by a factor of 10. Finally, out here, the distance is so large that in one calculation, Jupiter is on one side of the sun, in the other calculation, it's on the other side of the sun, and then they can't get any further apart than that, so the distance saturates. Here, they did the calculation over again, but they used more digits in the calculation, 80 bits instead of 53 bits, and the same effect happens. It just happens somewhat more slowly. So the conclusion from these calculations, is that all of the orbits of the planets are chaotic over very long time scales, and small changes in the orbits double every few million years. What does this mean? First, it means that we cannot predict the positions of the planets for more than about 50 million years, more than about 1% of the age of the solar system. Beyond 50 million years, we don't know whether at a particular time Jupiter will be on one side of the sun or on the other side of the sun. In fact, because chaotic systems are so sensitive to small perturbations, when any one of you came to this lecture, the change in the gravitational pull on Jupiter due to the mass in your body in coming here rather than staying at home is sufficient to change the position of Jupiter from one side of the solar system to the other in a few 100 million years. So it's very hard to predict. That means that on the longest timescales, all we can do is make statistical statements about the future of the solar system by running many calculations with slightly different initial conditions and asking what fraction of them have a particular fate. Physicists have now done these calculations, and what they find is that if you calculate the positions of the planets out to the time when the sun dies, most of the planetary orbits stay the same. The positions within the orbits are impossible to predict, but the overall shapes of the orbits are the same. But Mercury's orbit changes randomly. And in particular, again, if you look at the eccentricity, Mercury currently has an eccentricity of 0.2, and that eccentricity changes randomly over a large range. So as an example, this is a calculation of 2,500 solar systems where they changed the initial position of Mercury by a millimeter or two in different directions at different times. And this is the eccentricity of Mercury. The sun will die at about 7,000 million years, and you can see that the different simulations have produced eccentricities of Mercury from extremely high to extremely low. Now, one consequence of this is that since the same process must have happened in the past, this is probably why Mercury has a much larger eccentricity than the other planets in the solar system. The second consequence is that when Mercury's eccentricity gets this high, its orbit is so elongated that it's likely to either collide with Venus or fall into the sun. And that means that in about 1% of the possible solar systems that have been investigated, Mercury will undergo some catastrophic event. It could escape from the solar system, it could collide with the sun, could collide with Venus, it could collide with Earth. All of those happen in some of the calculations, and we don't know which one is right, but there's some chance that Mercury will be lost from the solar system before the sun dies. It also means that Laplace picked the wrong example for Laplacian determinism. The solar system is actually not a very good example of a system whose properties you can predict far into the future from knowing the conditions right now. And finally, and perhaps most interesting, it suggests that maybe what might happen to Mercury has already happened to some other planet in the past. Perhaps when the solar system was much younger, it had more planets, maybe 10 or 15, and that some of those planets were unstable like Mercury is and have already been lost from the solar system. We would have no evidence whether this has happened or not because the planets are gone, but it's quite likely that the solar system began with more planets and has been slowly losing planets as it settles into a more and more stable state. So the conclusions, I think, from what we know about the solar system are that we now understand the answer to this 300-year-old problem. The solar system is probably stable at the 99% level. The world will probably end in fire rather than in ice. That is, the Earth will probably remain in its orbit until it's burned up when the sun dies. But it's likely that the solar system was not stable in the past and that other planets have been lost. So let me now switch from talking about this problem that we now understand very well, where I can give you real answers, to a set of problems where I can't give you any answers, which is to try to apply the same techniques to try to help understand planets around other stars. And let me start by reviewing what we know about planets around other stars, because this knowledge has changed so rapidly in the last 2 decades. This is an image of the sun and 100 or so nearby stars. The nearest of these, Alpha Centauri, is about 3 light years away, 1 million times the distance of the sun. And what we would like to do, of course, is to look out around 30 light years for 100 or so nearest stars and ask if they have planets, ideally if they have planets like the Earth. This is a very hard job. The reason it's so hard is that the Earth and other planets are only visible in the light they reflect from the sun. The total light that the Earth reflects from the sun is only about 1 part in 1,000 million of the light of the sun. Jupiter is bigger, but it's also further away, so it's not much brighter. Now, if they were isolated, they would be easy to detect because even around nearby stars, objects of this brightness are easy to detect with modern telescopes. The problem is that they're right beside the sun. And the sun is so much brighter that it overwhelms any chance of seeing the planets. The example, which is pretty accurate, is to imagine that you're looking at a lighthouse to guide ships 1,000 kilometers away, and there's a firefly, small luminous insect flying around the light 1 meter away. That's equivalent to the problem of finding the firefly is equivalent to the problem of seeing a planet like the Earth. So the only way to find such planets is indirect. One indirect method is to recognize that according to Newton's laws, it's not quite true that the Earth orbits around the sun. The Earth and the sun both orbit around the center of mass of the Earth and sun. So the sun executes a small orbit around the center of mass, while the Earth executes a big orbit. And as the sun goes around the center of mass, because of the Doppler shift, the lines in the stellar spectrum moves back and forth a very small amount, periodically with a period of 1 year. Astronomers have developed the technology to measure these changes in the spectral lines very accurately. The current accuracy is about 1 meter per second. For comparison, if we were looking at the solar system from another star, Jupiter would cause the sun to move 13 meters a second, so that's easy to detect. Earth causes the sun to move by 10 centimeters per second, so that's impossible to detect with modern technology. Many stars have been looked at for these shifts, and by now we've found over 500 planets using this particular method. The second successful method works only if the planet happens to be orbiting nearly edge-on. If it's orbiting edge-on, once every orbit, it passes in front of the face of the star. When it does, the light from the star exhibits a small, sharp drop. As the planet orbits around again, there is a second, smaller drop when the star blocks out the light from the planet. And in between, there's an oscillation in the brightness caused by the phases of the planet, like the phases of the moon, which causes a small oscillation in the brightness as the planet goes around the star. The problem with detecting this effect from the ground is that stars twinkle. This is an example of a planet passing in front of a star. This has happened over and over again, and they have superimposed the results from many different orbits, all with the same phase. In this case, during the transit of the planet in front of the starlight drops by 0.5%. You can see that in any single passage, that's impossible to detect, and it's only by averaging over many passages that you can detect it. The great advance over this came from a spacecraft launched by NASA. By looking at stars in space, there is no atmosphere, so the stars don't twinkle. And this was a very simple spacecraft. It had a big camera, and it stared at the same set of about 100,000 stars continuously, 24 hours a day, 7 days a week for 4 years, and looked for these small dips in brightness. The star I showed you before, this is the data from the ground, from a telescope from the ground. This is the data from the same star as seen by Kepler. Again, you can see the dip when the planet passes in front of the star. The signal is much cleaner. If you increase the scale by a factor of 7, the signal still looks clean. And if you increase it by a factor of 100, the signal has more noise, but you can see the secondary transit as the planet goes behind the star, and you can see the oscillation in the brightness due to the changes in the phases of the planet. So with this spacecraft, we can now get much more information about planets from these transits. And Kepler has been extremely successful There are now over 3,000 likely planets discovered by Kepler. They're only likely planets because it has discovered so many that we don't have enough ground-based telescopes to check that they're all really true planets. So those two techniques, measuring the velocity of the star and the transits, are the way that most planets outside the solar system have been discovered. What have we learned? First and most important, we've learned that planets are very common. In particular, if you look at stars like the Sun, and you look for planets like the Earth, and like the Earth, in this case, means the radius is between 1 and 2 times the radius of the Earth, and the amount of sunlight that they receive is within a factor of 4 of the amount of sunlight that the Earth receives. If those are your criteria for a planet like the Earth, something like 15 to 30% of stars like the Sun have a planet like the Earth. This doesn't mean these planets have atmospheres. It doesn't mean they have oceans. It doesn't mean they have life. We can't tell. But with the crude criteria of the radius and the amount of sunlight, there's a lot of planets like the Earth. Planets like Jupiter are much bigger and might be harder to form, but even in this case, 5 to 10% of the stars like the Sun have a planet that's at least as big as Jupiter and at least as close to the star as Jupiter is. And these are not just single planet systems. Almost half of the planets that Kepler have discovered are in systems with multiple planets. That is where the spacecraft has seen more than one planet transiting the star. The second most important thing that we've learned about these planets are that the planetary systems we have found are very different from the solar system in many different ways. And let me explain some of the differences. This graph shows the orbital period of all of the planets that have been discovered by measuring the velocity of the star. This is the orbital period in years. Small orbital period means it's close to the star. Large period means it's a long way from the star. And this is the planet mass in units of Jupiter's mass. The most striking feature of the plot is that there's a big gap down here. That's a gap due to technology. Planets down here don't produce enough radial velocity in the star for us to be able to detect them. We also run out of planets here. That's simply because you can't reliably detect a planet unless you measure it for more than one orbital period. And the surveys have been going for 10 or 15 years, and so you can't detect any planets with orbital periods longer than 10 or 15 years. If I put the planets in our own solar system on here, there's Venus, Earth, Jupiter, and it's striking that no solar system planet, except maybe Jupiter, could have been discovered around another star. That is, if we took our technology and we're on a different star looking back at the Sun, we might have detected Jupiter, but none of the other planets. And even Jupiter is difficult mostly because its orbital period is so long that you have to have very patient extraterrestrials who will follow for 20 years to be sure they've found Jupiter. Another striking difference is that giant planets like Jupiter are found in far closer to the host star than in the solar system. Remember, Jupiter was out here. There's a large cluster of planets between about a third of Jupiter's mass and 3 Jupiter masses that are even closer to the star than Mercury. Some of these orbit their star in a period of a few days or even less. There is no example like this in the solar system, of course. So why are Jupiters so common, very close to the star in other systems, but not in our own? Another difference is that in our system, there's a gap between the biggest rocky planet, which is Earth, and the smallest giant planet, which is Uranus, about 15 times bigger. There are no planets between 1 Earth mass and 15 Earth masses, yet in other systems, there are many planets in this range that have come to be called super-Earths. We don't know what they're like. We don't know if they're rocky like the Earth because there's no analog to them in the solar system. There are also planets much bigger than Jupiter in other systems. You can see that there are planets here going up to 10 or 15 or 20 times Jupiter's mass, far larger than Jupiter. For some reason, you were able to form much bigger planets in other systems than in our own solar system. And the final and one of the most important differences, again, goes back to the shape of the orbit, to the definition of eccentricity ranging from 0 for circles to nearly 1 for very elongated orbits. This shows the eccentricities of all of the planets that have been detected against the orbital period. And you can see that there's a huge range of eccentricities. The biggest one here is around 0.95. That's a planet in this particular system. If you superimposed its orbit on the orbits in the solar system, there's Mercury, Venus, Earth. This would cross Mercury's orbit, come almost to Earth's orbit, and go in far closer to the Sun than Mercury does. There's no orbit like that for any planet in the solar system. In fact, if you look more carefully, if we put all of the planets in the solar system on this diagram, you can see that apart from Mercury, all of the other planets have orbital eccentricities that are much smaller than the eccentricities of most of the other planets. The solar system orbits are much more circular than the orbits in most of the other extrasolar planetary systems. Okay, so for reasons we don't understand, the systems we've discovered look very different from the solar system. But there's one more difference, which is even more surprising. I've described the two methods for detecting planets. In very rare cases, the same planet can be detected by both methods. That is, the planet transits in front of its star, and it also happens to be so massive that you can detect its effect on the star's radial velocity. In that case, you can learn much more about the planet and the system. In particular, stars rotate, and in a case like this, if you have a rotating star, this is the part of the star coming towards you, which I've colored blue. This is the part going away, which I've colored red. As the planet crosses in front of the star, it first blocks out the part coming towards us, then it blocks out the part going away from us. That means that the velocity curve of the star shows a sharp oscillation as the planet goes across it. The shape of that oscillation depends on the relative orientation of the planet's orbit and the spin of the star. In this case, where the orbit of the planet has an axis that's aligned with the spin axis of the star, the oscillation looks like this. As you tilt the planet orbit more and more, the shape of this curve changes. And from the shape of that curve, you can measure a quantity called the obliquity, which is the angle between the axis, the polar axis of the star, and the axis perpendicular to the orbit of the planet. This is an example of an actual observation. This is the brightness of the star, and you can see a very sharp drop of about 2% as the planet crosses in front of it. And on the same time scale, the velocity of the star is changing slowly from its motion around the center of mass, and then shows this sharp oscillation as the planet goes in front of it. From fitting this, you can determine that the obliquity, that is that angle between the spin axis of the star and the orbital axis of the planet, is almost zero, just like it is in the solar system, where the angle between the sun and the planetary orbits is only about 7 degrees. This measurement has now been done for about 50 stars. There is the sun down here. This is the angle between those two axes. And although some of them, maybe half the orbit axis and the spin axis are aligned. In all of the rest, there are huge misalignments. In these cases, the sun is actually spinning in the opposite direction that the planet is going around. Again, something very, very different from what we see in the solar system. What does all this mean? Well, we don't know, because we don't know how planetary systems are formed. But we have a rough idea. The reason you know that it's only a rough idea is because there are all these beautiful pictures that artists have drawn, and they all look different. But what we do know is that planets form from a rotating disk of gas and small solid bodies that's left over after the star is formed. Once the star is formed and begins to shine, the burning star burns off the gas in the disk. As illustrated here, it's burned off the gas in this region. We believe that planets form from the material in this disk, but they have to form quickly, within a few million years, before the gas is all burned out. Beyond that, we have a general idea of how planets form, but the formation is an extremely complicated process. It involves growing bodies by 40 orders of magnitude. Many aspects of how this process works are not well understood. Nevertheless, if we believe this general picture is correct, there are some very simple, strong predictions that we can make. So if the planets form in this general way from a disk of material around the star, they should form on nearly circular orbits, because the material in the disk is on circular orbits. The giant planets like Jupiter can't form close to the star with periods less than about a year, because the gas in the disk is too hot to condense into planets. And the planets should all orbit in the same plane, and that should be the same plane as the equator of the star. Now, one of the reasons that this theory was originally formed is that all of these predictions work very well for the solar system. The planets all have small eccentricities and inclinations. The giant planets have orbital periods of 10 years to 150 years. And the planets are all close to orbiting in the same plane, and that's very close to the equator of the sun. And what has been surprising is that none of these predictions work well for the systems we've discovered around other stars. So, for example, planets should form on nearly circular orbits. We've seen that the eccentricities of planets around other stars are much higher than in the solar system. Giant planets should not be able to form too close to the star, but we've seen that there's a large number of planets with masses even bigger than Jupiter's, forming in orbits of periods of only a few days, far closer to the star than even Mercury. The planets should orbit in the same plane as the equator of the star, and we've seen that in many of these systems there are big misalignments between the spin axis of the star and the orbital axis of the planet. Now, what does all this mean? Well, the simple answer is we don't know. However, we've seen that instabilities in the planetary system occurring long after the system was formed are likely to have happened in the solar system. And if similar processes happened in other planetary systems, they might explain these facts. In particular, collisions between planets will leave the planets on non-circular orbits, so they might explain why circular orbits are not so common in other systems. Close encounters between planets might scatter planets onto very eccentric orbits, and once they're on those orbits, if they come close enough to the star, they may circularize from tidal friction close to the star, so you might be able to explain the presence of planets very close to the star. If planets are scattered onto very eccentric orbits and fall into the star. If a giant planet like Jupiter fell into the sun, it would change the spin axis of the sun. And so again, the possibility of instabilities causing planets to scatter onto very irregular orbits might also explain why some of the stars have very high obliquities. We don't know if these are the correct explanations, but it's striking that all of the unexpected features that we've seen in extrasolar planetary systems are consistent with instabilities occurring long after the system was formed. And the hope of planetary theorists is that they will be able to tell to what extent the properties of extrasolar planetary systems are caused by these instabilities. Okay, let me summarize what I've been trying to say. I've talked about two problems. One is a very old problem for which we understand the answers. The other is a set of new problems for which we only understand the questions. We now understand the answer to this question from 3 centuries ago of whether the solar system is stable. The answer is that the orbits of the planets in the solar system are weakly chaotic. That means that small changes in the orbits double more than 1,000 times in the lifetime of the solar system. As a result, the positions of the planets are not predictable over timescales longer than about 50 million years, about 1% of the age of the solar system. That means that the question of whether the solar system is stable can only be answered statistically, and the statistical answer is that there's a 1% chance that any of the planets in the solar system will be lost before the sun dies. However, it's much more likely that planets have been lost from the system in the past. The questions we have are about trying to understand the many planets we've discovered around other stars. Many features of these systems are very different from the solar system, and some of those features may arise from long-term instabilities in the systems. What we hope to do over the next decades is first to understand the variety of possible extrasolar planetary systems. We're still constrained by the technology. As I said, with current technology, if we looked at the solar system from outside, we could only detect Jupiter. There's much more work to be done in the technology to understand what kinds of planetary systems we could form. And once we understand that, we hope that that will give us enough clues that we can understand how planetary systems and how the solar system formed. For my final slide, I wanted to show a picture that you've all seen. This is a picture of the Earth taken by the Apollo astronauts on the way to the moon back in the 1960s. If you ask almost any researcher who is working on extrasolar planets what their ultimate long-term goal is, they will almost all say, our ultimate goal is to produce a picture like this of a planet around another star. The technology to do this is not available yet. It will be many decades before we have any hope of getting a picture like this. I'm sure I will not see such a picture in my lifetime, but I think there's some chance that some of the youngest people in the audience may either see such a picture or be able to remind their grandchildren in turn to look for such a picture sometime in the future. When we do find such a picture, I think it will be one of the really great accomplishments of our civilization and will have an influence on our culture and civilization even greater than this picture did 40 years ago. Right, thank you.